A webinar on machine learning, deep learning, hands-on experiments. RDBS Geeta Deep Enterprises. In association with Sharad Institute of Technology, College of Engineering, Ichokaranji. Sponsored by Institution of Electronics and Telecommunication Engineers.
Welcome to Day 6 MLDL webinar. Today we are going to modify VGG16 output layer. Yesterday we are seeing how to call VGG16, how to download it first and then call it, and then how to use it for feature extraction purpose. Today we are going to configure or modify VGG16 outputs, and we are going to retrain it using a CI/FAR dataset, and we are going to check its performance. So let's begin with the experimentation.
So now let's begin. From TensorFlow Python, import VGG16. Even if today also if you are not downloaded VGG16 model, this command will download it from applications. VGG16 you have to call. Save this and run it first. So I will save it in new day 5 folder with new name MyPro VGG16 mod, because we are modifying VGG16 today. Next to that, run this using command window. Python MyPro VGG16 modbot.py. So this will check first that if model is available, otherwise it will download. Next to that, from TensorFlow .python .keras .applications .vgg16 import pre-processing input. Next to that, import image from layers. You have to import you are going to redefine input. Also we will be in the need of flatten and dense layers at the output. So in between layers we are going to keep as is. We are going to modify input and output. Next to that, model import, just like yesterday. Next to that, import numpy as np. Then call model VGG16, or simply we will name model only to avoid extra typing. Assign it VGG16. So if it is pre-trained, we don't want to use pre-trained weights, or if you want to use pre-trained, you can use ImageNet also. Next to that, whether you want top layer or not, here we are setting it to false, and then we are trying to print the summary first. Let's run it. Yes, image I think is capital we have written. So yes, here I. Well, you have to be very specific while importing particular, and for that you must have to use Google. So as now if we have called ImageNet to use pre-trained weights, this is going to download, okay, and it's around 58, so I'm skipping the part because I have already downloaded partial ImageNets. We are not going to use ImageNet weights. So here simple weight layered model, just like yesterday we have printed. Now let us redefine input. So we have called input from Keras layers. So the argument required for input is shape. So the shape of your data you have to mention here. So this is 3 by 22, 224 by 224 color image it is, and the name of input should be, you can redefine input. So we define image input. So while printing the summary, the name will be printed as image input. So here it will get replaced by our new value. Next to that, here I am typing some reference that what we have done. Next to that, output you can redefine. So output is whatever the output of model with respect to input. Our name is model, not VG16. So when we give 224 by 224 by 3 image as an input, we will get actual output from VG16 just like yesterday. Now we want to add fully connected layers. So one of the method we are trying to understand first, that how to add fully connected layers in our network. So first layer we want to add is flatten, because last layer is a dense layer, second last layer. So the name should be given for each layer so that identification while printing the summary becomes easier. And what should be the input of this layer is nothing but output of previous model. Next to that, x is equal to dense with the name, you can specify your own size requirement, with the activation function as ReLU, rectified linear unit. Next to that, you have to specify the name of the layer. So FC1 we define here, and the input of this layer is output of previous layer. Again, x is equal to dense, similar type of layer. So here it becomes more accurate processing as the number of dense layers goes on increasing. but it does not mean that you will go on increasing the way you want, otherwise computational complexity will go on increasing. So the name FC2 we are giving here with the input which is output from previous layer. So now x is equal to dense as the final output we can define with the activation function as a softmax. Always output layer should be activated by softmax function, do remember, for better output and to avoid some decimal class names, and the input should be output of previous layer. So this is going to be our final output layer of the model. Next to that, we define my model equal to model inputs equal to input, which is predefined earlier. Next to that, this input is this one, do remember. Next to that, output is equal to outputs, which is predefined. So here we complete our modification in VGG16. So I think almost we have written everything correct. Let me cross check. Yes, here x should be the output, not the output that we have predefined. So correction is made. Now my model dot summary to check the architecture. So let's run it. You can also completely remove the last layer of output is not defined error is coming. Okay, some corrections we need to make. Again same error coming, so we need to change. Yes, argument type is plural sense, inputs and outputs. So yes, now we have got our own model in which we have embedded VGG16 model. So you can see image input, then VGG16 embedded here, then flatten, FC1, FC2 and prediction layers. So this way how we can modify the VGG16 for getting desired output as per our required application. Next to that, we will extend this experiment for classification. So we will copy and paste all this data in the new file and rename it with the new name for new application. Yesterday we had used MNIST data. From that file we have the data loading strategy and all this. So this commands for the import library. here we paste at the start. Next to that, data loading in terms of shuffled manner for training testing, then reshaping, pre-processing, then normalization, then categorical of the labels. So now, as we have copied and pasted this MNIST, so let us change the data MNIST to CIFAR 10, because CIFAR is the three-dimensional color image data. So while loading also you have to change this CIFAR 10. Due to this command, the database will be downloaded inside pip cache of Keras, so of Python for Keras compatibility. So this dataset is around 1.7 GB length. Next to that, we are having the size of CIFAR image as 32 by 32. So these changes we have to establish in today's program. Next to that, while calling VGG16, we can change the input method equal to input, where we are defining input is equal to input with shape equal to 32, 32, 3. So now this input is responsible to call VGG16 model with the way we want as the input layer should be. So it is now ready to receive 32 by 32 by 3 image. Earlier it was 224 by 224 by 224 image as per basic VGG16. So here we have now modified. So now let us first compile our model. Here my model is set with this one. Here one modification, you do remember that the last layer of the VGG16 is removed, and from second last layer, whatever the output is, there we are attaching our this layer, that is tens fully connected network, again one more fully connected network, then flattening, and then we want 10 class output from this data set, so whose activation should be softmax, and we are naming this layer as a predictions. So here giving input this flattened output from previous dense layer. So my model, with respect to model input, the model defined here is VGG16 earlier assigned. The input of that should be input to this model, and output of x, output defined in terms of x, should be given here as x. So here is our new my model. So we can print the my model summary. Next to that, we are going to load the xtrain, ytrain, xtest, ytest using load method of Keras from CIFAR 10 dataset. Next to that, the reshaping from whatever the loaded to 32 by 32 by 3, and the first argument will be nothing but images. So that for that we will convert into float 32, then divide it by 255, so it will become a normalized data. Next to that, ytrain and ytest are converted into categorical. Now it's time to compile. So my model dot compile command, just like we had called while learning MNIST dataset, you can compare our this program with that one also. Loss equal to categorical cross entropy, and optimizer equal to Adam and matrix equal to accuracy we consider here. So you can refer the yesterday's program also, the day before. So here we had written one compile command. Yes, simply you can copy paste for the just to avoid the errors. But here only the model name is my model, so we make the correction. Next to that, my model dot fit with respect to x train, y train, whatever the data is. So you again we will copy the earlier command here with the NB approach 2 and batch size 1. So this way. Now let us run the program. You must compile your model before training testing. Use model.compile. So here we have missed the my model call, so now it should run. Yes, now it is running perfectly. So around estimated time is 3 hours, as this is 3-dimensional data. So you can understand why high configuration machines are required in deep learning applications, and especially for image processing, or even if you are going for dataset processing, there is such a huge time requirement if your machine configuration is not proper. Even in my case, I have i5 processor, 8 GB RAM, and that's why this much time is been shown. So further, and this is a 3rd generation processor. I'm not using right now 6th generation processor for this experiment. I also have 6th generation, but there is not much difference because RAM equality and all, and that's why people used to shift onto the GPU models, and because of which this processing time will get reduced much, at almost by 50% minimum. So here I break the processing now. Now it will be your part, your side work, that to complete this output. Next to that, you can also check the score like we had for MNIST dataset. Here we will again copy and paste this last command to print the score. So here we complete our VGG16 loading, modification and retraining for our own dataset and checking its performance.
So this way we can modify VGG16 model and we can retrain it to obtain the performance that we want. Today we have added 4 more layers at the output using flatten and dense layers. So you can also add your own layers to form or to extend the network up to the layers you want. Be sure that you are not losing actual features data while extending the network layer. So up to here only we stop. Thank you.